지금은 이제 한국에 하는 사람이 많아서.
Of this morning session is Professor Hwang DongSeon from Aju University. He will speak about log-Delpechov surfaces of rank 1.
Thank you. So first, I would like to thank the organizer for invitation to this nice environment. Yeah, I'm also an organizer, but I did not invite myself. I was invited by other organizers, so. Okay, so today I will talk about log-Delpechov surfaces of rank 1. So this is my plan of the talk. So first, I would like to define what log-Delpechov surface is, and I'll give you some easy examples and known classifications. And then I will state the main result of this talk. And the proof is based on Mianish-Zhang's theory. So actually, it is published by, actually this is the result of Zhang's PhD thesis under the guidance of Mianish. So I will explain the theory, and I'm going to complete, in some sense, complete his theory, and using that to prove this main theorem, the classification of all such surfaces. And if time permits, then I will consider the Delpechov surfaces with worse singularities. So by worse mean Delpechov surfaces with some non-rational singularities or general rational singularities or log-Delpechov pairs, the non-zero boundary. Okay. So first, I will talk about log-Delpechov surfaces. So okay, so I will walk over the field of complex numbers always because this concept quotient singularity is quite nasty in positive characteristics. Okay, so this is the classical definition. A normal projective surface S with quotient singularities is called a log-Delpechov surface if the anti-canonical divisor is ample. Okay, so this is very classical. And this minimal positive integer R such that minus RK is Cartier is called an index. This is called a Cartier index or a Gorenstein index in the literature. So I will just call it an index. Of course, there is a more general notion called the log-Delpechov pair. We are considering the surface and an effective divisor D on it, but this will be considered later. Okay, and this log-Delpechov surface is called of rank 1 if the Picard number is 1. Okay? And if you attended the lecture of Professor Jong-Hae Kim's lecture, then every log-Delpechov surface of rank 1 is a Q-homology projective plane with quotient singularities. Actually, we can redefine this log-Delpechov surface using this Q-homology projective plane. So a surface is a log-Delpechov surface of rank 1 if and only if it is a Q-homology projective plane with quotient singularities such that the anti-canonical divisor is ample. This is another definition. And long before, I think more than 35 years ago, Mianish observed this fact. So let X be a normal projective surface with quotient singularities. And assume that X is a Picard number 1. Then X is a log-Delpechov surface of rank 1 if and only if the log codial dimension of the smooth locus is negative infinity. Okay. So actually I will give you many examples of log-Delpechov surface of rank 1 later. And every time I give you a log-Delpechov surface of rank 1, if you remove the singularities, then you will get a Q-acyclic surface whose log codial dimension is negative infinity. Okay. So by this, yes. I don't know about this Platonic C-star vibration. Yes. What is your question? Yes. So, okay, so something is wrong. But this is proven by Mianish, and there is a complete proof in the paper of Zhang. So we'll discuss it later. Okay, because I don't know much about this Platonic C surface, so I think it's. Sorry. It satisfies my assumption. So maybe yeah, he said the result is correct anyway. So. So we'll discuss it later anyway. So I will not use this factor anyway. Okay. Okay, so these are the basic examples. P2 is the only smooth example. And this every weighted projective plane is a typical example because the Picard number is 1 and anti-canonical divisor is ample. And every normal projective toric surface of Picard number 1 has ample anti-canonical divisor. So all those are examples. So this is not true, of course, if the Picard number is higher than 1. And every finite group quotient of P2 is also an example of such surfaces. And there are also many. Those are the basic examples. So the aim is to provide a method to produce every one of them. So before going further, I want to review the Gnome classification. So this is for general log-Pezzo surfaces. According to the lower index, so if the index is 1, in this case, it is called Gorenstein-Pezzo surface. So it means that the surface only have AD singularities or Dubar or rational double points. In this case, there are many contributors here. So Brenton has initiated this study. Actually, he was interested in Q homology P2, but every example that he constructed is an example of a Gorenstein log-Pezzo surface of rank 1. And Hidaka and Watanabe completely classify those surfaces. And they also provide the explicit equations in some weighted projective space. And soon after, Alexeyev and Nikulin, they completely classify the index 2 case. So actually, their method is quite different. So they considered K3 surfaces with non-symplectic involution. And there is a one-to-one correspondence between those surfaces and log-Pezzo surfaces of index 2 by quotient by this non-symplectic involution and take some resolution. Okay, so there is a complete classification, and Kapuska brothers has provided all the weighted equations for them. And later, Nakayama, he used MMP technique to classify all log-Pezzo surfaces of index 2, even in the positive characteristic case. Okay. So index 2 case satisfactory, and index 3 case, Uhashi and Taki, they generalized the method of Alexeyev Nikulin. So they classified all K3 surfaces with non-symplectic automorphism of the order 3, and they classify the corresponding log-Pezzo surfaces of index 3. But in this case, there is no such a good one-to-one correspondence. So the log-Pezzo surfaces of index 3 that are coming from this K3 surface is quite a few. So this is not so satisfactory. And later, recently, Fujita and Yasutake generalized the method of Nakayama, and they have succeeded in classifying all such surfaces of index 3. And recently, Alessio Corti and Huiberger, so as a test case of Corti's program of classifying Fano varieties using mirror symmetry, they considered 1/1/3 1/1 singularities. And okay, so there are some results. Okay, so this is the recent progress about this classification according to the row index. The main difficulty lies in those. So the proof gets very complicated as the index increases by following this Nakayama, Fujita, Yasutake. This MMP process is really complicated. So as far as I know, they are no more working on this case. Actually, Corti is interested in generalizing their method to the higher index case, but they are not doing it anymore. And the other problem is that the index is not bounded. So in this way, we have to go forever. Okay, so I'm going to consider only Picard number 1 case. So there are two main methods to classify those surfaces. The first is the Mianish-Jiang's method that I'm going to speak later. And the other one is the MMP. Okay, so there are many people devoting to this business. So I'm going to review it later. And Kier and McConnell, they kind of classified all log-Pezzo surfaces of rank 1 in many cases, but it is not very explicit. And later, Hecking and Prokhorov used Kieran-McConnell's method to classify all such surfaces having Q-Gorenstein deformation. And toric case is quite nice. So now we have a good classification. So they classified all such surfaces, all toric such surfaces up to index 16. And this proof depends on computer. And as far as I know, this 16 can be enlarged. So for any given positive integer n, we can classify them up to the index n. But you know, this index is not bounded anyway. Okay, so okay, in this case, rank 1 case, the following is known. So Hideo Kojima, the previous speaker, classified the unique singularity case. And we know that Belosov, who is a former student of Prokhorov here, he showed that the number of singular points is bounded by 4. So now the remaining case is 2, 3, and 4, basically. So as Professor Kim said earlier, we have classified those surfaces with 4 singularities and H1 of the smooth locus is 0 to give a proof of algebraic Montgomery-Yang problem for the log-Pezzo surface case. And later, here we later used lattice theory very much. We used Dechi-Zhang's method, but not very many. But here, completely relying on this Dechi-Zhang's method, I have classified with maximum singularity case. But the proof is quite complicated, so I decided not to publish. And in the process of simplifying the proof, I got the idea. So this is what I'm going to talk about today. Okay. Here the main difficulty is that there are too many cases. So I'm going to give you the method of constructing them to illustrate this difficulty. Okay. So this is the most easiest one. So several ones are easy. So so take a line on the projected plane, just blowing up any one point. Then you have Hilbert surface F1 here, and blowing up this point, you get this. Blowing up this, you get this point. So here you have blown up 3 points from P2. So the Picard number is 4, and you have contracted those 3 minus 2 curve. So this says Picard number 1. So this is the example of a log-Pezzo surface of rank 1, having A2 and A1 singularities. Okay. And starting from this, if you blow up this point, the minus 1 curve, then you have this configuration, and now you have 4 minus 2 curves. And if you contract them, you will get another example of a log-Pezzo surface of rank 1 with A4 singularities. In this way, downstairs you will get many log-Pezzo surfaces of rank 1, and upstairs you will get the minimal resolution of those. Okay? So this is a typical way of constructing log-Pezzo surfaces. And so the easiest way of constructing log-Pezzo surface of rank 1 is from Hilbert surface. Okay, so every log-Pezzo surface of rank 1 is known to be rational. So there is a morphism to P2 or Fn. So this is easiest. So take a Hilbert surface and take the negative section and a fiber, and do the similar thing. Blow up this point, and you will have this configuration. If m is 2, it is exactly the same as before. So you will get a log-Pezzo surface of rank 1. But here, before you have blown up this minus 1 curve, a point on minus 1 curve that is not lying on those minus 2 curves. But here, actually, we have 3 choices. In the middle point, if you blow up the middle point, you will get this configuration. And if you blow up this intersection point of minus 2 curve and minus 1 curve, then you will have this configuration. So anyway, after contracting those negative curves, you will get many different log-Pezzo surfaces of rank 1. Okay? This is very well known and very easy ways to constructing. So you can do the similar thing for 2 fibers, 3 fibers, 4 fibers. But you cannot go further, because if you use those 4 fibers to do that, then you will have 5 singular points. It is contradictory, but the thing is, the one thing here is not a quotient singularity. Actually, this is LC singularity. Professor Kojima has classified So it is known that the log-type patch surfaces of rank 1 having only log canonical singularities can have at most 5 singular points, and this is the unique case. So Professor Kojima has proven it. Okay, so this is the easiest way, and now we review the construction from P2. So take general 3 lines on P2 and blowing up those 3 intersection points and blowing up those 3 points. So we have taken 6 blown up. And now we have 6 minus 2 curves here. So by contracting them, we will get log-type surface of rank 1 with 3 A2 singularities. And we can do the similar thing. Or by blowing up the points on this minus 1 curve, we will get many other log-type surfaces this way. So until now, it is an easy ways to construct it. Okay, this is the first example of a complicated one. So now take 3 general lines and 1 more special line passing through the intersection point here and here, and take another nodal cubic with very special configuration. So it has tangency to this line, and we have nodal in this point, and tangents 2 here, tangents 2 here. Okay, take this. Then if you blow up this point, you will get Hilbert surface. So basically, this is 2 sections and 3 fibers, and the proper transform of the cubic lies this. So if you follow this process, then you will get this. So eventually, you will have the configuration of 4A2. So here we have 1, 2, 3, 4, 5, 6, 7, 8. 8 blow-ups. This is the exceptional divisor. Yes. So here, minus 2 and minus 2, this one. So this one goes to 1 singular point here. So we take 8 blow-ups and 8 blow-downs, 8 contractions, so we have the log-type surface of rank 1, having 4A2. Okay? And actually, there are many more delicate ways to get another log-type surface 1 from this configuration. And there are many more such configurations, such very delicate configurations to produce log-type surface of rank 1. So this is the main difficulty, why it is quite hard to find them all. Okay, now I'm going to introduce my result. Oh, it's not. Anyway. So before explaining my result, I want to introduce the notation. So S is always a log-type surface of rank 1. And S prime is its minimal resolution. And D here is the F exceptional curves, the exceptional divisors, and reduce the exceptional divisor of them. And R, from now on, R is no more index. R is the number of singular points. And I will use this notation, S sub x. This is the set of all log-type surfaces of rank 1 whose singularities are of type x. So, for example, S sub 4A2 is the last example of both. Actually, there is only one log-type surface of rank 1 having this singularity type. So, the last example, this set is nothing but this set. So basically, Mianish-Zhang's theory is not about the classification of log-type surfaces. It's about the classification of the singularity types on those surfaces. Okay, so the determining singularity types of S is nothing but determining the configurations of D on S prime. D is the tree of exceptional divisors. Reduce the exceptional divisors. Okay, before explaining my result, I want to review the Gorenstein case first. So if the Picard number is 1, there are exactly 27 possible singularity types for Gorenstein case. And moreover, Xiang Ye, who is a former student of Zhang, he also determines the kind of moduli of those surfaces. So actually, in many cases, I mean, except 4 cases, the singularity type uniquely determines the surface. And in those 3 cases, there are exactly 2 surfaces having this configuration, having this. Oh no, there are some, yes. Yes, and and for 2D4, there are infinitely many such surfaces. This is coming from the construction. Okay, and it is not very related, but generalizing this result to Q homology projective plane, as Professor Kim said, there are 58 possible singularity types for them. And they all have one-dimensional moduli. So it says that the behavior is quite different from this case and that case. I mean, the anti-canonical divisor is ample or canonical divisor is snap. The minimal moduli case and the modifiable space case, the behavior is quite different. Okay, now I'm going to state my result. So if the Picard number of the minimal resolution is at most 2, then it is very easy to see that the log aperture surface is either the projective plane or the cone over the rational curve. It is very easy to prove. So we can assume that the Picard number of the minimal resolution is at least 3. Okay, so this is the theorem. I have to explain many things, but anyway. So with the same notation, if the Picard number is at least 3, we have one of the 3 cases. So S is either a Gorenstein log aperture surface, so they only have AD singularities, or S is of KT type. I'm going to explain it, what it is. So KT is Kojima Takahashi. So Kojima is, yeah, I have to refer Kojima many times anyway. So otherwise, there exists a -1 curve C, such that the blowdown of C induces a morphism from this S prime to T prime, where this T prime is this is a minimal resolution of another log aperture surface of rank 1 with somewhat milder singularities. Okay. So some remark. So if S is Gorenstein, then this minimal resolution admits a morphism to P2. And for KT type, this admits a morphism to Fn. I'm going to, yeah. And except for 3 cases, this -1 curve C is actually a minimal curve. Minimal curve in the sense that minimal up to this degree. Okay, this is the ample left divisor, and if this intersection number attains a minimal positive value, then we call it a minimal curve. And we can take it as a minimal curve, such that the intersection number is at most 2. Okay, it can meet only twice of the, at most twice of the exceptional divisors. Okay, using that result, now we can do the classification. So this one is kind of a generalization of Taichi-Jiang's method, and using that, we can classify all such surfaces. So with the same notation, every minimal resolution of a log aperture surface of rank 1 can be obtained from basic surfaces. So this basic surface is a kind of subclass of Gorenstein or KT type surfaces by basic blow-ups. So basic blow-up is basically what we did before. So for example, if we have this configuration, then in the previous example, we have blown up, oh, you cannot see this? Then some choices, you can either blow up this point to get another log aperture surface over that point. So basic blow-up is nothing but those kind of blow-ups on the minimal resolution of log aperture surfaces. And so every minimal resolution of log aperture surface of rank 1 can be obtained in this way. And conversely, every surface obtained by this process is actually a minimal resolution of a Q-homology projective plane with quotient singularities. So actually, in the converse process, the amplitude of the anti-canonical divisor is no more true. So we'll get more complicated surfaces by this inverse process. But actually, I can completely characterize the case when this Q-homology projective plane becomes log aperture surface. I mean, I can determine every case such that the anti-canonical divisor is ample. So this gives the complete classification of all such surfaces. Okay. And actually, the minimal resolution of a log aperture surface is a Mori-Dream space. So there are only finitely many -1 curves. So there are actually finitely many choices for these blow-ups at each step. Okay. So those are basic surfaces. So here, every such surfaces can be obtained from basic surfaces. So those are basic surfaces. So so there are 13 types. And for the first 7 types, those are nothing but Gorenstein log aperture surfaces having those singular points. Okay. And the others are of KT type, Kojima-Takahashi type. And if you look at very carefully, then you will immediately construct them from the Hilbert surface. Okay? So those are the cases. And basic blow-up is nothing but those kind of blow-ups. So from that, you can blow up this point, that point, or something like that. And in this way, you will get every such surfaces. I can hear you, sorry. Yes. I have never considered that before. Yeah, maybe. Maybe. Yeah, right. So in this case, yeah, probably you are right. I never thought about it. Okay. Okay. So from now on, I'm going to explain the proof. So how many minutes do I have? 25. Okay. Okay. First, I'm going to review what is known for this Mianis-Yang theory, and then I'm going to explain my extension of those theory, and I will apply it to the theorem. But since this is some part of it is very technical, so I'm not going into detail, but I'm happy to explain the detail after the talk. Okay, so I will define the minimal curve first. So any irreducible curve on the minimal resolution is called minimal if the degree is minimal. I mean, this degree according to this degree is minimal. Okay, this is natural to consider. But yeah, maybe. Maybe. Yeah, right. So in this case, yeah, probably you are right. I never thought about it. Okay. Okay. So from now on, I'm going to explain the proof. So how many minutes do I have? 25. Okay. Okay. First, I'm going to review what is known for this Mianis-Yang theory, and then I'm going to explain my extension of those theory, and I will apply it to the theorem. But since this is some part of it is very technical, so I'm not going into detail, but I'm happy to explain the detail after the talk. Okay, so I will define the minimal curve first. So any irreducible curve on the minimal resolution is called minimal if the degree is minimal. I mean, this degree according to this degree is minimal. Okay, this is natural to consider, and it always exists actually because if you have a log-Pezzo surface, then you have index R, and this has value in this set. So you will have this minimal positive value anyway. So it always exists, and it's not unique in general. In some examples, sometimes it's unique, but sometimes it's not. Anyway, we know that there are only finitely many because it's a origin in space, and there are many ways to prove it. Okay, so the aim of this theory is to classify all configurations of CND. I mean, the weighted dual graphs of the exceptional divisors and together with this minimal curve. And we'll separate the case into the two cases. So we consider this linear system, C plus D plus KS prime. So the linear system D plus KS prime is always empty. So we consider those two. Okay. So we first consider this non-empty case. So this was starting from Daechi-Yang's PhD thesis and his first paper, and there are some improvements. So in this case, by basically using Zariski decomposition and some Riemann-Roch theorem, we can prove that if SS are singular points, then R minus one of them is rational double points. So they are simple. And the other one is just a cyclic singularity. Actually, this cyclicness is coming from the next one. And and using this Zariski decomposition argument, we can prove that sim is the last component only at twice. Okay, so the only possibility is like this is the last one, and C should be of this form to make it a what is that? I forgot. Chain. Cycle. So thank you. Cycle. And the exceptional case is like this. So sim is like this. Tangency 2, or this, or this. Okay, so those are all the possibilities of the configuration. And we can have more components which corresponds to the rational double points. And also Belousov proved that C is always a smooth rational curve in this case with self-intersection number -1 or 0. So here the remaining task is to know the self-intersection number of each of the irreducible component of those. If we know all the self-intersection number of those, then we are done. But this is not easy. So actually, Dechi-Zhang reduced the classification test to the quasi-Itaka surface. But for me, it is almost impossible to understand. This is really complicated for me. So I'm not using this, but I will use another method. And now we consider the empty case. In this case, Belousov proved that C is a smooth rational curve. So this is a -1 curve. This is nothing but Riemann rock in this case. And of course, using Riemann rock, we can prove that each connected component of D at most once. So this minimal curve C can touch at most once of the singular points on the singular surface level. And it can meet at most three components of the exceptional divisors. And it's getting complicated, but so there are at most 3 of them. So let them we denote them by DI. Okay. So if C meets the exceptional divisor only once, then the self-intersection number should be -2. This is very easy anyway. And similarly, it's not very hard to get those. So we have those cases. And it's not very convenient to write using this notation, so I will adopt this notation. So the minimal curve is of type A1 through AN. If C meets D at n points, and the self-intersection number is given in this way. Okay? So this one is, in this case, the minimal curve is of type 2,2. This is 2n, something like that. Okay, so after this observation, Dechi-Zhang actually prove it. It's very natural to consider. If C meets D at 1 point or 2 points with the type 2n, n is greater than 2, then there exists a -1 curve C, such that the blowdown of C gives a morphism from the minimal resolution to a minimal resolution of a log-type surface of rank 1. So this is exactly what I mentioned before. In this case, this is very trivial because if we meet -2 points once, then if you blow down, then you will get this one. So it's very easy to see that. And so the remaining case is not very easy. I mean, if CD is 3, then we have fallen this case or this case. And for this case, it is very hard. So actually, Professor Gurja and Dechi-Zhang deeply studied those cases. So there are many restrictions now, but still, there are too many cases for that. So okay, and the other cases are completely classified by Kojima and Takahashi, but under the assumption that there is no minimal curve C such that those. So actually, in reality, there are examples that there are many minimal curves such that some minimal curve have this property and some minimal curve have this property. But he only classified only in this case. Okay, from now on, I will explain my results. So in the non-empty case, I quite satisfactorily classified them. So in this case, we have three cases, and if CD is 3, then surprisingly, S is one of 2 cases in Kojima, Takahashi, or they can be obtained from the surface from here. So actually, the latter case, there are only 3 cases for the latter case. So this is so if CD is 3, then this is either Kojima, Takahashi, or those 3 surfaces. Actually, this was already mentioned by Professor Kim before. But okay, so those are all -2, and these are -1. So you can easily construct it from the Hilbert surface. So this is, you see that there is a A1 singularity here, triple singularity here, and quintic singularity here, and there is EA singularity above. Okay. So, and there are some more. So, maybe it's better to use this notation. So those 3 are the only exceptions. But in this case, of course, we can contract this minimal curve C to get another one. So in this way, you easily see that you will get this configuration. So 3A1 plus D4 that I mentioned there. Okay, just oh no. Okay, so this is different one. And if you contract this one, this -1 curve 3 times and this one once, then you will get this one. Okay, but also if you contract this minimal curve C, you will also get another one. So eventually it goes to E8 anyway. So either way, you can go to this Gorenstein case. Okay, so there are two difficult part in this proof, in the whole business. So this is one of the most difficult part. So the thing is, I'm sorry, but this is only for expert. So if CD is 3, we can consider some divisor called G. There are 2 cases. This case where it can be linearly equivalent to another -1 curve. What I did was, this case actually doesn't exist. And there are only 3 cases for this one, that one. So this is actually what I did. And the main ingredient of the proof of this thing is an intersection theoretic formula. Actually, it's coming from the lattice theory. So basically, this is related with this 4-dimensional topology stuff, describing this configuration. So I don't have enough time to explain it because this is very delicate, but after the talk, I can explain if you want. Okay, so for the non-empty case, we have several rational double points here, and one possibly non-rational double point, cyclic singular point. So let D prime be this irreducible component, and let L be the number of irreducible component of that connected component. In this case, Belousov proved that this is either a -1 curve or a 0 curve. And what I prove is it is actually always a -1 curve. If there is a configuration like that and C is a 0 curve, then this cannot be a minimal curve. If it is not Gorenstein. Yes. Anyway, if it is a 0 curve, then this is not minimal. This can be also proven by this intersection theoretic formula. Okay, so in this case, we have those low L cases and this case. So for low L cases, there are exactly 26 cases. And in this case, I can exactly construct it from P2. So I have a full understanding of those. So we can prove that. Okay. Yes. And if this is 3, so this is, for me, this was the most difficult part. But I succeeded in proving this. So in this case, either S is Gorenstein, or there is another minimal curve C, such that this linear system is empty. So we can pass from this non-empty case to the empty case. Okay. Yeah. So in this case, S is Gorenstein, or we have this case, but the latter case happens only for 2 cases, and it can also be described very explicitly. So I can obtain them from Kojima-Takahashi surfaces. Okay, so this is the kind of completion of Miyanishi and Zhang's theory, and using that, I'm going to classify them all. So so basically, this is an induction on the Picard number of the minimal resolution. So first, I have a log-delta surface of rank 1. Take a minimal resolution. Okay, and then S is Gorenstein or of KT type, then we are done. So assume that it's not. Okay, now we find a minimal curve. It always exists, and it turned out to be a -1 curve. First, consider this case. And if CD is 3, then there are only 3 cases we have proven in the previous proposition. And if it has at most 2 intersection points, since it is not of KT type, we can always blow down this -1 curve to get the same situation with one less Picard number. So we can go back and do this process again. Okay, so now there is no minimal curve with empty such a linear system. So the linear system is non-empty. Now, if R is at most 2, as I said before, there are exactly 26 cases, and we already treated them. And if L is at least 3, then by the previous proposition, S is Gorenstein. So it is done. So if you follow this algorithm, then it is either done, or you can come back to the first step with one less Picard number. And since the Picard number is finite, if the process ends with finite remaining steps, so that we have the complete proof of the theorem. Okay. For the remaining time, I'm going to talk about the Pezzo surfaces with worse singularities. So how many minutes do I have? 9 minutes. Oh, thank you. So I was quite fast than I have expected, but anyway. Okay, thank you. Okay, so actually, to be honest, I didn't precise this last part very much because I expected I will be lack of time, which it turned out to be false. But actually, recently, 3 years ago, Kojima and Takahashi extended the theory of Miyanishi-Zhang to include those rational low canonical singularities. So, yeah, rational low canonical singularities. So it properly contains the quotient singularities. And if you follow the proof, then this proof also works when S allows to have rational low canonical singularities, not just K or T singularities. But the only remaining case is this one, but it can be anyway analyzed using the formula. So we can actually extend the result to have those rational low canonical singularities. But actually, if the Pezzo surface of Picard number 1 has a non-rational singularity, then those are completely classified. And actually, every non-rational low canonical Pezzo surface is of Picard number 1, and this is nothing but the contraction of the elliptic ruled surface. So it seems that now if we completely analyze those cases, then we have a complete classification of Del-Pezzo surface of Picard number 1 with low canonical singularities. And so the remaining case is this case, Del-Pezzo surface with general rational singularities. So in this case, the possibility of the dual graph is can be really complicated. So I'm not sure if it is possible, but Ivan Chesov actually want me to try this, but I'm not sure. Maybe I will let my students do that. Okay, so this is the situation when the boundary divisor is 0, and this is for general one. Now we consider the pair. Consider this log pair S, D. So we call it a KRT log Del-Pezzo pair. If S is normal projective surface with KRT singularities, so we can replace it by LC here if you want. And D is an effective Q divisor on S, such that minus K minus D is ample. Okay, so if the boundary divisor D, here KLT is nothing but quotient singularity. It's the same here. Kawamata log terminal. Here it is exactly the same as quotient. So if D is 0, then this one, and this is nothing but the surface that we have been considering so far. So actually, we have this result. So let S be a smooth projective surface. Then this pair, and consider, sorry, so I missed one condition here. So consider a log pair S, D, S, delta. And then this log pair is a KRT Del-Pezzo pair for some effective Q divisor delta, if and only if the anti-canonical model is a KRT log Del-Pezzo surface. So this KRT log Del-Pezzo surface is nothing but the log Del-Pezzo surface in the first part. But actually, 30 years ago, Fumio Sakai has analyzed this anti-canonical morphism. So every such anti-canonical morphism is decomposed by the minimal resolution of a Del-Pezzo surface with rational singularities, followed by a sequence of so-called redundant blowups. So this is another subject, so I don't want to define it. But anyway, this redundant blowup is recently completely classified by me and Jin-Hyung Park. So yes, not this Jin-Hyun Park, but Jin-Hyung Park. But anyway. Okay, so what does this result say? The result says that the classification of all such log Del-Pezzo pair when the surface is smooth is reduced to that of log Del-Pezzo surface in the previous sense. So now we have a quite good understanding on this pair if this surface S is smooth. So the redundant blowup can be explained, but this is kind of another thing. So I would like to stop here. Thank you for listening.
Are there any questions or comments?
Yeah. Of course, it's a good invariant to try, but I've never thought it before. So maybe after talk we can discuss. I've never thought about it.
I see. And another question is that if you have these surfaces of homology of E2, and you go out, your C was had homology of E1, right?
Yes. C is just a smooth rational curve.
Yeah, and it's something ample, right?
Yes.
So if you throw it out, you get something affine with Euler C1.
I guess so.
I'm not sure how often you get something geocyclic, but
Yes. I'm actually interested in those questions. Right.
yeah, because we know really a lot about these geocyclic surfaces, so maybe you rely on the results.
Right. That's right. Yes. Right.
So,
That's right.
any other questions or comments? Okay, if not, let's thank the speaker again. Okay. Thank you.